Okay, I'm going to continue from where I left off. So again, we are using Gay-Lussac's law, which is the relationship between pressure and temperature when the volume is being kept constant. Okay, so this is exactly why you do not throw an aerosol can into a fire, and oftentimes aerosol cans have a warning on them saying, flammable, keep away from an open flame. This is why. So let's say an aerosol can is thrown into a blazing fire, okay? So this is going to be our T2, because that's after throwing it into the fire, okay? So that's the after, okay, that's the final. Before it was thrown into the fire, it had a pressure of 4 atm and 27 degrees Celsius. So our initial pressure was 4 atm and our initial temperature was 27 degrees Celsius, because that was before, so that's the initial. So we're trying to find out the pressure. We're going to say that's going to be in atm. That's what we're going to find it in. And we know that the temperature after was 402 degrees Celsius. So again, we have our, this should be P2. So we have our initial conditions, what the can started at, its pressure and temperature. Again, the can, it's an aerosol can, it has a fixed volume, so that's not changing. And then we have our conditions for after it was thrown into the fire. Okay, so we're going to plug into our equation. However, before I even do that, you need to convert anything that's in degrees Celsius into Kelvin. So if you remember the equation, Kelvin equals degrees Celsius plus 273.15. So to get these degrees Celsius into Kelvin, I just have to add 273.15. So you're going to be doing this quite a lot. 273.15 plus 27 is 300.15 Kelvin. And then plus 273.15, 273.15 plus 402, so that's 675.15 Kelvin. Okay, so now I can plug into the equation. So I have my P1, which is 4 atm, over my T1, which is 300.15 Kelvin, is equal to, again, this is the equation I'm using, is equal to our X, which we're trying to find in ATM, which it'll be in ATM because that's what this pressure is in, 675.15 Kelvin. So in order to solve for this, we're going to cross multiply to solve for X, okay? So 300.15 Kelvin times our X is equal to that 675.15 times 4. So that's 2700.6, okay? So we cross multiply, and then we have to get X by itself, so we're going to divide each side. Again, so this is, for these units, this is ATM Kelvin right now. Again, you don't have to put the units in the equation, but I like to do it so then you can see how those units would cancel out so that you're just left with the unit you want your answer in. So we're going to divide each side by 300.15 to get the X by itself. So that will give me, if I go 4 significant figures, 8.99, so this would be 8 ATM. So then the application question is, if the maximum pressure of the aerosol can is only 8 ATM, will the can explode? Yes, because it is above, its final pressure is above the maximum pressure that the aerosol can withstand. So that's why you don't throw something like that into a blazing fire. All right, let's continue with another problem using Gay-Lussac's law. All right, so a rigid plastic container, so that means that the size of the container will not change. It has a fixed volume, so the volume will stay the same. Holds 1 liter of gas at a pressure of 0.9 atm. And then again, it does, and then the temperature is 22 degrees Celsius. What will the temperature change be in degrees Celsius if the pressure decreased? So the volume part actually isn't really relevant for this question because it is going to be kept constant the whole time. So our starting pressure is 0.9 atm and our starting temperature is 22 degrees Celsius. Again, the first thing I'm going to do is convert this into Kelvin right away. Because again, whenever you're plugging into these equations, you need to make sure that your temperature is in Kelvin. So 273.15 plus 22. So 295.15 Kelvin. And then our pressure, after we have changed the temperature, okay, there's been some type of a change in the temperature. Our new pressure is now 0.7 atm, and we need to solve for, okay, our final pressure is 0.7 atm. So we need to solve for the final temperature. The final temperature, it needs to be in degrees Celsius. However, we need to plug into the equation in Kelvin, and then once we get our answer in Kelvin, we can convert it back into degrees Celsius. All right, I'm going to plug into my equation. So I have my P1, my initial pressure is 0.9 atm. My T1, my initial temperature is 295.15 Kelvin, is equal to our final final pressure, which is 0.7 atm. Both of our pressures are in atm, so that's great. And then we're going to be solving for our T2. So again, we're going to cross multiply. So 0.9 atm times our x is equal to, so we have to do that 295.15 times 0.7. So 206.605. And again, this is atm and Kelvin. To get x by itself, we're going to divide both sides by 0.9 atm. Again, you don't have to include the units in the equation when you're plugging things in. I just find it easier to make sure that my units are canceling properly, and then I've converted all of my units that I've needed to convert before I plugged into the equation. So I'm going to take that 206.605 divided by 0.9. So we're going to go 4 significant figures, so 229.6. Again, right now this is in Kelvin, okay? However, the question was asking for the final answer in degrees Celsius. Well, to go from Kelvin to degrees Celsius, you just have to subtract 273.15. So this would be negative 43, which you can have a negative degrees Celsius. You can't have a negative degrees Kelvin. 59 degrees Celsius. And that would be my final answer. So again, when you're plugging in to the equation, you need to plug in the temperature in kelvins, because that's what these equations, that's what they were based on. It needs to be in Kelvin. So you might have to convert degrees Celsius into Kelvin, plug that into the equation. You're going to get your answer in Kelvin, and then you can easily convert Kelvin back into degrees Celsius to get your final answer, if the question was asking for the final answer in degrees Celsius.